Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today, longest repeating character replacement, Leetcode 424. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given a string S consisting of uppercase English letters and an integer k, and we can choose any character of the string and change it to any other uppercase English letter, and we can perform this operation at most k times. Then our task is to determine the length of the longest substring containing the same letter we can get after performing the above operations. Then in example 1, for the given string and k equal to 2, we can modify the string to have all the same characters by changing these b's to a's, giving us the string AAAA, or changing these a's to b's, giving us the string BBBB. Both transformed strings are the longest possible results we can get, where all characters are same, and since we need to return the length of such a string, the answer is 4. Similarly, in example 2, for the given string and k equal to 1, we can replace one character in the string to form the longest substring. And suppose we replace this b with a, where we will get the longest substring as AAA, or we can replace this a with b and get the substring BBBB. And since we need to return the length of such a string, the answer is 4. Now in terms of solution, one straightforward naive approach could be that we generate all possible substrings of the given input string by using two nested loops, say with iterators I and j, and for each starting index I, we iterate through all possible indices and extract the substring. For example, for this substring starting with A, we can form the substring like A, AA, AAB, and so on. And then starting with the second A, we generate the substrings like A, AB, ABA, and so on. And this process is repeated for every character in the string, treating each as the starting character. And for each substring, we check if it is homogeneous, that is, if all the characters match or can be made homogeneous with at most k replacements. We'll discuss how to perform this check shortly. And if the substring is indeed homogeneous, then we track its length, and the maximum length among all such homogeneous substrings gives the final answer. Now let's see how we can check the homogeneity. For that, let's take some example to make it clear. Substrings A and AA are already homogeneous, so they don't require any changes. But let's take the substring AAB, and suppose k is equal to 2. Now, how can we make this substring homogeneous? Well, we have two choices. Either we convert the b's to a's. This will require one replacement, resulting in string AAA. Or we convert all the a's to b's. So this will require two replacements, resulting in string BBB. Now, which of these is more optimal? Since we have a limited number of replacements, it makes sense to convert the less frequent characters into most frequent ones. In this case, converting a B to A is better because fewer replacements are needed. Also, instead of this k equal to 2, if we had k equal to 1, then replacing A's to B's wouldn't even be possible. So we can only replace B into A, leading to homogeneous substring AAA. So, what does this mean for this problem? For a substring to be homogeneous, all its characters must match the most common or most frequent character after replacements. And how can we figure this out for any substring? Well, we can create a frequency map. So for each substring, we count how often each character occurs. For example, for this substring, we can see that A occurs twice and B occurs once. Now the most frequent character here is A, which occurs 2 times. And how do we find the maximum frequency of any single character in the substring? We will just iterate over the keys of the frequency map and select one with the maximum frequency. And as the map has only 26 characters, this whole operation will take O of 26 or constant time. And the length of this substring is 3. So that means we have to replace one character in the string to make the whole substring homogeneous, where all the characters are same as the most frequent one. And given k is equal to 1, we can easily make this change. and get the homogeneous substring. And in general, if this difference is less than or equal to k, that is the number of replacements required are less than or equal to number of replacements available to us, we can easily make the substring homogeneous. And iterating over all substrings, we can determine the maximum length of a homogeneous substring that can be achieved. Now, even though this approach works, it is not very efficient in terms of time complexity because generating all the substrings require nested loop which takes O of n squared time, and for each substring calculating the frequency map takes another O of n time. Hence the overall time complexity will be O of n cube and the space complexity will be O of 26 or O of 1, because in the worst case for each substring frequency map stores only 26 uppercase English letters. Hence the overall space complexity will be O of 1. And now that we have understood the naive approach, let's think about whether generating all possible substrings is really necessary. For example, suppose we are processing this substring with k equal to 1. Now this substring is invalid because it has 3 A's and 2 B's, and out of these 2 B's, say we replace this B to A, but the second B cannot be replaced as we have already used one replacement allowed by k, and so the substring cannot be made homogeneous. So now, do we really need to check the remaining substrings starting with this A? The answer is no, because any subsequent substrings that includes this invalid substring will only grow longer and remain invalid. So a better approach is to think of a substring as a window within the original string where all characters are homogeneous. This window starts small and grows exponentially, and we have to find the largest window we encounter during the iteration. The two ends of this window are represented by 2 pointers. Left pointer, which marks the beginning of the window, and right pointer, which marks the end of the window, indicating the current character being processed. Initially, both left and right pointers begin at the start of the string at index 0. At this stage, the window contains only a single character, which is naturally homogeneous. But programmatically, to check if the window is valid, that is, it is either homogeneous or can be made homogeneous, we can keep track of a frequency map as introduced in the naive solution with a small change that since we are only dealing with 26 uppercase English letters, instead of frequency map, we can use a frequency array which will hold the frequencies or counts of characters in the current window. And the index in the array corresponds to uppercase English letters from A to Z. For example, index 0 stores the frequency of A, index 1 stores the frequency of B, and so on. And finally, index 25 stores the frequency of Z. And to calculate the index of the given character, we can simply subtract capital A from the character. Initially, all the frequencies are 0. Now let's see how the sliding window will work. So, initially both left and right pointers are at the start of the string where we see character A, and so we increase the frequency of A at index 0 to 1, and the length of the window is also 1, which can be given by the formula right minus left plus 1, because both right and left are inclusive, meaning the window contains all the characters from index L to index R. Now the maximum frequency we encounter in this window is also 1. So number of replacements we require are 0, which is less than k. So this window is valid, and hence we will expand the window further at the right to find even longer window, and we encounter another A. So now the frequency of character A is 2, which is also the maximum frequency. And how can we find that? One way is to loop through this frequency array to find the maximum frequency. This will take O of 26 or constant time, since the array only contains 26 uppercase English letters. But a slight optimization can be that since when we are expanding at right, the only character that recently was added was A, so the frequency will only change for this character A. Rest of the frequencies will stay as is. So we can easily calculate the maximum frequency by taking the maximum of the current maximum frequency and the frequency of this character just added at right Hence, we can save some time with this optimization. Now, the maximum frequency is 2 and window length is 2 as well. So, number of replacements required will be 2 minus 2 equal to 0, which is less than k. So, the window is still valid and hence we expand the window at the right and this time we see the character B and increase the frequency of B to 1. Now, window length is 3 and the maximum frequency will be the maximum frequency we have seen so far, which is 2, or since we added B recently, we only updated the frequency of B, which is 1 and is still less than maximum frequency. So maximum frequency will be again 2 and the replacements required will be 3 minus 2 equal to 1, which is less than equal to k. So this is also a valid window and hence we will expand the window further on the right where we encounter another A. So the frequency of A becomes 3 and window length is equal to 4 and maximum frequency is 3 and the replacements required will be 4 minus 3 equal to 1, which is again less than equal to k. So this was a valid window as well and the homogeneous string we can form is with 4 A's and this is the longest valid window we have seen so far, which we try to expand even further. Now, frequency of B will be 2, but the maximum frequency will be 3 and the length of the window will be 5. Hence, the replacements required will be 5 minus 3 equal to 2, which is more than k this time. So now the window has become invalid since replacements required exceed k available replacements. So at this point, we have to make the window valid somehow and that we can do by shrinking the window on the left where this character A goes out of the window. So the frequency of A reduces to 2 and ideally maximum frequency would also update to 2. We can do this by looping through the frequency array which takes constant O of 26 time since there are only 26 uppercase letters. However, we can optimize this process by not updating the maximum frequency when shrinking the window. Why? Because our goal is to find the length of the longest valid substring found so far, and reducing the maximum frequency won't help us achieve a longer valid substring. Let's break it down a bit. The condition for a valid window is that window length minus maximum frequency should be less than equal to k. And rewriting this, we get window length should be less than equal to k plus maximum frequency. This shows that to maximize the window length, we need the largest possible maximum frequency as k is constant. And in the algorithm, we have three phases. First is growing phase, where we expand the window to the right and both window length and maximum frequency increase as we are searching for largest possible valid window. Then comes the plateau phase, where we eventually expand the window to a point where it becomes invalid. And at this stage, we have already found the maximum possible valid window length for the current maximum frequency. And finally comes the sliding phase, where we shrink the window at left and try to make the window valid again. But here's the catch. If the character we remove at the left pointer was part of the majority, the actual maximum frequency of the window might decrease. For example, here, where the character A at the left pointer was part of majority, and removing it reduces the maximum frequency from 3 to 2. But reducing the maximum frequency would also shrink the maximum window length possible, and any future valid window would then necessarily be shorter. So by not updating the maximum frequency downwards, the algorithm says that my current best window has length x achieved with maximum frequency m, and I will no longer consider any window shorter than x unless I find enough characters to create a new maximum frequency larger than m. And this optimization ensures we only search for longer valid windows without wasting time recalculating frequencies for potentially shorter ones. However, during the interview, it is often better to stick to the simpler approach of looping through the frequency array, which even though takes O of 26 time, but still a constant time, which is not a performance bottleneck. So, window length is again 4 and the maximum frequency is 2. So, the replacements required are still 2, which is more than k, so the window is still invalid, and we shrink it further, which reduces the frequency of a to 1, while maximum frequency remains 2, and the window length is 3. So number of replacements required is 3 minus 2 equal to 1, which is less than equal to k. So now the window is valid again. So we expand the window at right, where we encounter character b and increase the frequency of b to 3. And now the maximum frequency is 3 and window length is 4. So number of replacements required are 4 minus 3 equal to 1, which is less than equal to k. So this is also a valid window. So we expand the window further, where we encounter character a. Now number of a's become 2 and window length is 5 and the maximum frequency is 3. So number of replacements required will be 5 minus 3 equal to 2, which is more than k. So we shrink the window further and reduce the frequency of character b to 2 and the window length becomes 4 and the maximum frequency is 2. So number of replacements required is still 2, which is more than k. So the window is still invalid. So we shrink the window further and reduce the frequency of letter a to 1 and now the window size becomes 3 and the maximum frequency is 2. So number of replacements required is 3 minus 2 equal to 1, which makes the window valid again. So we will expand the window further on the right and now the right pointer exceeds the string length. So the iteration ends and the maximum valid window length encountered during the iteration is 4, which we will return as the answer. Now the time complexity of this approach is O of n. Because the right pointer iterates through the string, processing each character exactly once, and the left pointer moves forward only when the window becomes invalid, ensuring each character is considered only once by both pointers, and the space complexity will be O of 1. Because for each window, we are using frequency array consisting of only 26 entries, which is constant, to keep track of the character counts. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on left and Python on right. First, let's create a frequency array of size 26 to store the occurrences of uppercase English letters. Next, let's initialize the answer to keep track of the maximum valid window length. Now, let's define the left pointer, which starts at the beginning of the string, and iterate on the input string using right pointer starting from 0 to the end of the string. This pointer expands the window to the right. Now, first we calculate the index of the character at the right pointer by subtracting literal a from it and increment its corresponding count in the frequency array. Now, we check the validity of the window. So we check if the difference between the window length, which is given by the formula right minus left plus 1, and the max frequency exceeds k. If that is the case, then the window is no longer valid. So we shrink the window by incrementing the left pointer and decrement the frequency of the character being removed and continue to do so until the window becomes valid again. That is, the difference between the window length and the maximum frequency is within the bounds of k. And once the window becomes valid again, we calculate the current window's length and update the answer to be maximum of its current value and this current window length. And once the loop finishes, all the characters in the string has been processed and answer will hold the length of the longest valid repeating character substring, which we will return in the end. And here we are recalculating the maximum frequency by looping through the frequency array, which takes constant O of 26 time. However, instead of recalculating, we can update the maximum frequency incrementally when the right pointer moves and a new character enters the window. But we don't decrement the maximum frequency when shrinking for the reasons explained earlier. And this code should run a bit faster, maintaining the correctness while simplifying the logic. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.